Chapter 23 Electric Potential. Units of Chapter 23 include electric potential energy and potential difference, relation between electric potential and electric field, electric potential due to point charges, potential due to any charge distribution, equipotential surfaces, electric dipole potential, electric field E determined from V potential, electrostatic potential energy, the electron volt, cathode ray tube, TV and computer monitors, and oscilloscopes. Section 1. Electrostatic potential energy and potential difference. The electrostatic force is conservative. Potential energy can be defined. Change in electrostatic potential energy is negative of work done by electric force. Here on the left, we have a demonstration of two charge plates, which are uniformly distributed of the charges, and they are separated by distance d. And we see in the middle we have a uniform parallel electric field is formed between these two charge plates. So we have on the left we have a high potential energy point and a plate of a high potential, and on the right we have a low potential energy and a low potential point is shown with spot A and B are the representations of points with high potential and low potential respectively. So the electrostatic potential energy is shown with U at point B and A. If we subtract these two, we have UB minus UA, which is equal to minus W minus the work, and is equal to minus Q times E times D. Electric potential is defined as potential energy per unit charge. So V sub A is equal to U at point A. So the electric potential V is equal to the potential energy divided by Q unit charge. The unit of electric potential is the volt, represented as V. So 1 V is equal to 1 joule per coulomb. Only changes in potential can be measured, allowing free assignment of V equals 0. So if we say VBA is delta V differential of the electric potential is equal to V at point B minus electric potential V at point A, and is equal to the electric potential energy UB minus UA, energy at point A, divided by unit charge Q, and that is equal to minus WBA, the work done from point B to point A, divided by Q. There is an analogy between gravitational and electrical potential energy. Here on the left we can see this is a representation of some piece of stone which are raised to height h, and they obtain gravitational potential energy, U as m, the mass of the stone, times g, the gravitational acceleration, times h, the height which the stone has been raised. On the right we have the electrical potential energy, which is represented with U, and this is a difference between the points with potential VB and point with potential VA multiplied by the charge. Electrical sources such as batteries and generators supply a constant potential difference. Here are some typical potential differences, both natural and manufactured, listed in table 23-1. Some numbers and some items might be familiar to you. For example, the electric potential difference for an automobile battery is 12 volts, or the typical flashlight batteries is 1.5 volts. And we can have all the way up to thundercloud to ground, that's the discharge of a lightning to the ground, and that is 10 to the power 8 volts. Okay, example time. Problem number 6 in the book. Part A. A proton with a charge of Q equals plus E and a mass of 1.67 times 10 to the power minus 27 kilogram accelerates from rest in a uniform electric field of E equals 4.5 times 10 to the power 4 Newton per Coulomb for 36 centimeter. What speed does it attain? And B, through what potential difference was the proton accelerated? All right, so since the electric field is uniform, the proton will observe a constant force, and therefore we will observe a constant acceleration. The initial velocity is 0 because it starts to accelerate from rest. So we can say V0 is equal to 0. And the displacement is delta x. That is 36 centimeters, right? So we can use equation 211 and write down F external is equal to mass times acceleration. And here the force is equal to charge times the constant uniform electric field. We can solve it for acceleration, charge times electric field divided by mass. And from here, we can solve it for acceleration. Also, we know that the velocity for an accelerated kinetic movement is equal to initial velocity, V0, plus the square root of 2a delta x. Okay, let's plug in the numbers. V0 is 0. We should say the square root of 2 times a, which is q e divided by m times delta x. Let's plug in the numbers. The square root of 2 times charge is 1.6 times 10 to the power minus 19 Coulomb times the electric field is 4.5 times 10 to the power 4 Newton per Coulomb times the distance is 0.36 meter divided by the mass of the proton is 1.67 10 to the power minus 27 kilogram. And as we simplify things, the velocity, the final velocity of the proton will be 1.762 times 10 to the power 6 meter per second. Which is almost 1.8 meter per second. For part B, field is uniform and the magnitude of the potential difference can be found from conservation of energy. We call the final position at the 0 volt location. The initial energy is all electrical potential energy and the final energy is all kinetic energy. So we have Q times delta V as the initial electric potential energy, and it should be equal to 1/2 mv final squared, velocity final. So from here we can solve it for delta V is 1/2 mvf squared divided by Q. Let's plug in the numbers. We have in the numerator the mass is 1.67 times 10 to the power minus 27 kilogram times the velocity that we just obtained. Let's put the exact number, 1.762 times 10 to the power 6 meter per second squared divided by 2 times 1.6 times 10 to the power minus 19 Coulomb. That simplifies to delta V equals to 1.62 times 10 to the power 4th volts. almost 1.6 10 to the power 4 volts. That is the answer. Section 2. Relation between electric potential and electric field. The general relationship between a conservative force and potential energy, as described as UB minus UA, the electric potential energy at point B minus energy at point A, is equal to minus the integral from A to B of the force F dotted with dl, which is the representation of the distance displacement from point A to point B. And this is shown in the figure on the right, which we show the red lines as the field lines, the electric field lines E, and we're moving from point A to point B, and at each spot we have a displacement vector dl, and it should be dotted with electric field vector, and we should integral from point A to point B. Substituting the potential difference and the electric field, we have VBA, which is the electric potential from point B to point A, VB minus VA, is equal to minus the integral from E to B of electric field E dotted with dl. The simplest example is a case of a uniform field, where the electric potential is given as electric field, which is constant, and gets out of the integral multiplied by the integral over the distance from A to B, which is a constant of d also. So the total electric potential is minus E times d. The electric potential can be given as a function of distance from the surface of a charged conducting sphere, which is plotted here on the right and compared with the electric field. So on top we have the electric field E as a function of distance from the center of the sphere with radius r. The electric field depends on r as 1 over r squared, while for the electric potential V, the dependence is 1 over r. The electric field is 0 from 0 to r, the surface of the conducting sphere, but the electric potential is constant, and the electric field, it goes high and it starts to be very strong on the surface and goes to 0 as r goes to infinity with the relation of inverse of r squared, while for the electric potential is a constant from 0 to r naught and goes as 1 over r as r gets farther away from the sphere. All right, let's look at problem number 14 in the book as an example. The electric potential of a very large isolated flat metal plate is V naught. It carries a uniform distribution of charge of surface density sigma with the unit of coulomb per meter squared, or sigma half, on each surface. Determine V at a distance x from the plate. Consider the point X to be far from the edges and assume X is much smaller than the plate dimensions. From example 22.7, we know that the electric field produced by a large plate is uniform with the magnitude of sigma divided by 2 epsilon naught. Okay. So the field of these large metal plates at point X on top of it is pointing away from the surface if the charge distribution on the surface is positive. And if we use equation 23, for A, we can say V at point X minus V, the potential at point 0, is equal to Vx minus V naught, and that is equal to the integral from point 0 to point X of electric field times dl And we can say that is equal to minus, I forgot the minus here, the minus, the integral from point 0 to point x of the electric field, which is sigma times 2 epsilon naught, and it's along I direction, let's call it x direction this way, I hat, okay, dotted with dl, and dl is also along x direction, so we can substitute this one with dx I hat. Okay, I hat gives a 1, and everything is constant, takes out, so we have the integral of dx gives us from 0 to x, and it gives us x, so we have minus sigma x divided by 2 epsilon naught. So v as a function of x is equal to v naught minus sigma x divided by 2 epsilon naught. Section 3. Electric potential due to point charges. To find electric potential due to a point charge, we integrate the field along a field line. VB minus VA equals to minus the integral from RA to RB of E dot dl. That is equal to minus Q divided by 4 pi epsilon naught, the integral from RA to RB, 1 over R squared dr. And that gives us 1 over 4 pi epsilon naught, which is the constant K, multiplied by Q divided by RB minus RA. Setting the potential to 0 at R equal infinity gives the general form of the potential due to a point charge. V equals to 1 over 4 pi epsilon naught multiplied by Q divided by R, and this is with the assumption of single point charge, and the potential is 0 when the potential is 0 at R equals infinity. Okay, let's look at problem number 32 from the book as an example. How much voltage must be used to accelerate a proton radius of 1.2 times 10 to the minus 15 meter, starting from rest, so that it has sufficient energy to just touch a silicon nucleus. A silicon nucleus has a charge of plus 14 electron, and its radius is about 3.6 times 10 to the minus 15 meter. Assume the potential is such as that for point charges. Here we have to assume that all of the energy of the proton gains is in being accelerated by the voltage is changed to potential energy, just as the proton's outer edge reaches the outer radius of the silicon nucleus. So as this is the radius of a proton, this is the radius of a silicon nucleus, and their separation is R, which is the summation, the radius of silicon and the radius of a proton. So we say the initial potential energy should be equal to final potential energy, and we don't have any kinetic energy because it starts from rest and it touches a silicon nucleus. So the initial energy starts from rest and there's no kinetic energy, and finally it reaches at rest and it doesn't have energy, kinetic energy, just the potential energy conversion from initial to final. So for the initial case, we have electric charge times the initial voltage. The initial potential is equal to 1 over 4 pi epsilon naught times the electric charge of a proton multiplied by 14 electron of the charge of the silicon nucleus divided by R, and R is the separation between the two nuclei. So we can solve it for the initial potential, and this is equal to 1 over 4 pi epsilon naught times 14 electron charge divided by R. Let's plug in the numbers. It's equal to 8.99 times 10 to the power 9 Newton meter squared divided by Coulomb squared multiplied by 14 times 1.6 times 10 to the minus 19 Coulomb divided by 1.2 plus 3.6 times 10 to the power minus 15 meter, and this is the sum of the radius for the nucleus of silicon plus the radius of proton nucleus. And if we do the calculation, the potential initial is equal to 4.2 times 10 to the power 6 volts. Section 4. Potential due to any charge distribution. The potential due to an arbitrary charge distribution can be expressed as a sum or integral if the distribution is continuous. So we have VA equals to sum for I equal 1 to n VI, that is equal to 1 over 4 pi epsilon naught, the sum for I from 1 to n QI divided by RI to A. Or if the distribution is continuous, we have electric potential V equals to 1 over 4 pi epsilon naught, the integral of dq over r. Let's look at problem number 36 from the book as an example. A total charge Q is uniformly distributed on a thread of length L. The thread forms a semicircle. What is the potential at the full circle center? Assume V equals 0 at large distances. All the charge is the same distance from the center of the semicircle. So the radius of the semicircle, as we assume, this is a semicircle, the radius is r, and all the charges have the equal distance of r from the semicircle. We can use equation 23(6b) to calculate the potential. Let's write down L equals to pi r naught, and r naught, this is r naught, and r naught equal to excuse me, L divided by pi. So the electric potential V is equal to 1 over 4 pi epsilon naught, the integral of dq over r, and r is a constant, is equal to r naught, so it takes out of the integral, so you have 1 over 4 pi epsilon naught L divided by pi, the integral of dq. And if we take the integral of all the charges, charge distribution, we will have total charge that is equal to pi q divided by 4 pi epsilon naught L. The pi's will cancel out. So the pi's cancel out, and we have the integral over q dq is equal to q. So we have q divided by 4 epsilon naught L. Section 5. Equipotential surfaces. An equipotential is a line or surface over which the potential is constant. Electric field lines are perpendicular to equipotentials. The surface of a conductor is an equipotential. So on the left we will see two charge planes, which we assume these are very large compared to the separation. and the electric field is constant. And if we draw a dash line, the green lines, perpendicular to the red lines of the electric field, we will see we have lines of equal and constant potential, electric potentials. So here, for example, we have 0 voltage, 0 potential on the negative plane, and we are increasing the potential 5 volts, 10 volts, 15 volts, 12 volts, all the way to the positive plane. But the green dash lines represent the equipotential surfaces and lines. Equipotential surfaces are always perpendicular to field lines. They are always closed surfaces, unlike field lines which begin and end on charges. Here we can see a dipole consisting of a plus, a negative, and positive charges. The field lines are originating from the positive charge and they are all the way to the negative charge, so they are beginning and ending on charges. Over these field lines, we have the green dash lines representing the surface of constant potentials or equipotential surfaces. And these are like closed surfaces. These are like lines perpendicular to electric fields. A gravitational analogy to equipotential surfaces is the topographical map. The lines connect points of equal gravitational potential or altitudes. Let's look at problem number 44 from the book as an example. A metal sphere of radius r0 equal 0.35 meter carries a charge of Q equals 0.5 microcoulomb. Equipotential surfaces are to be drawn for 100 volt intervals outside the sphere. Determine the radius r of A, the first, B, the 10th, and C, the 100th equipotential from the surface. So to solve this problem, we should refer to some prior knowledges to calculation. We know that potential at the surface of the sphere, let's put it down this way, at the sphere is equal to 1 over 4 pi epsilon naught Q over R naught. And the potential outside the sphere is equal to 1 over 4 pi epsilon naught Q over R, which is equal to V R naught over R is, this is a sphere with the radius R naught, and at any point outside this radius, outside this sphere, the distance from the center is R. So R is changing, but when we reach to R naught, the potential becomes constant. The potential outside the sphere is decreasing as we move away from the sphere. The difference in potential between a given location and the surface of the sphere is to be multiple of 100 volts. Let's write it down for the sphere, for the surface of the sphere. Let's put here V naught at the sphere is equal to 1 over 4 pi epsilon naught Q divided by R naught. So we have 8.99 times 10 to the power 9 Newton meter per coulomb squared, multiplied by Q is 0.5 times 10 to the power minus 6 coulomb divided by 0.35 meter, right? And it simplifies to V naught is equal to 12,800 43 volts. This is the potential at the surface of the sphere. Okay, now the problem says equipotential surfaces are to be drawn for 100 volts interval. So we should see at what radius, at what distances are the equipotential surfaces will form with 100 volts. So we say V naught minus V, and that is equal to V naught minus V naught R naught divided by R, and that should be equal to 100 volts times N, and represents the first, the tens, the number of the surface, the equipotential surface. So we can solve it for R. R is equal to V naught divided by V naught minus 100 volt times N multiplied by R naught. So now let's solve it for different surfaces, different N that the question is asking. So for example, part A, it says the first, so N should be equal to 1, and if we solve it, let's plug in the numbers. For V naught, we have 12,843 volts divided by, the V naught is the same, 12,843 volts minus 100 volts multiplied by R naught, and R naught is 0.35 meter. So we'll have 0.3527 meter, which is about 0.35 meter. It's almost on the surface, so the first equipotential surface is almost on the surface of the sphere. Let's go to part B, which is tens. N is equal to 10. Let's plug in the numbers. 12,843 volt divided by 12,843 volts minus 100 volt times 10 times 0.35 meter. And if we simplify, that is equal to 0.3796 meter, which is almost 0.38 meter to the significant digits. For part C, N is equal to the 100th equipotential surface. For this, we will have 12,843 volt divided by 12,843 volt minus 100 volt multiplied by 100 times 0.35 meter. That gives us 1.581 meter, which is almost 1.6 meter away from the center of the sphere. That concludes the problem. Section 6. Electric dipole potential. The potential due to an electric dipole is just the sum of the potentials due to each charge and can be calculated exactly. For distances large compared to the charge separation, here we have a point P, which is far away from the charge separation L, and point P is a distance almost equal to R, because R is much larger than L. We have electric potential V is equal to 1 over 4 pi epsilon naught Q times L cos theta divided by R squared. And that is equal to 1 over 4 pi epsilon naught P, the electric dipole moment, times cos theta divided by R squared. Section 7. Electric field E determined from electric potential V. If we know the field, we can determine the potential by integrating. In varying this process, if we know the potential, we can find the field by differentiating. EL, electric field along L direction is equal to minus dV divided by dL, the derivative of electric potential with respect to L. This is a vector differential equation. Here it is in component form. So we have Ex, electric field component along X, is equal to minus partial V partial X. The same for Y, we have minus partial V partial Y. And along Z direction, Ez is equal to minus the partial derivative of V with respect to Z. All right, let's go through problem 48 from the book as an example. What is the potential gradient just outside the surface of a uranium nucleus, Q equals to plus 92e, whose diameter is about 15 times 10 to the power minus 15 meter? The potential gradient is actually the negative of the electric field outside of a spherically symmetric charge distribution. The field is that of the point charge at the center of the distribution. Okay, so we say dV dr, which is the gradient of the potential, and that is equal to minus E, which is minus 1 over 4 pi epsilon naught charge Q divided by R squared. Let's plug in the numbers. We have minus 8.99 times 10 to the power 9 Newton meter squared divided by Coulomb squared. Multiplied by the Q is 92 times 1.6 times 10 to the power minus 19 Coulomb divided by 7.5 times 10 to the power minus 15 meter. So should be squared. The diameter is 15. We're talking about the radius, so we make it half. So dV dr, which is the derivative or the gradient of the electric potential, is equal to minus 2.4 times 10 to the power 21 volt per meter. Another example, let's look at problem number 50 in the book. It says the electric potential in a region of space varies as By, constant B multiplied by the y coordinate divided by a squared plus y squared. Let's write it down this way. By divided by a squared plus y squared. So V is a function of y, and it asks determine the vector E, electric field. So from equation 23(9), we know that we have to take the derivative of electric potential to calculate the components of electric field. So Ex is equal to minus partial V partial X. There is no X dependence of electric potential, so this is 0. Ey is equal to minus partial V partial Y, and we have some dependence, so it's non-zero, and Ez is partial V partial Z, and this is equal to 0. There's no Z dependence. So we only have Y dependence. Let's calculate this one. Ey is equal to minus partial V partial Y. Let's take a derivative of electric potential V with respect to Y. So we have minus partial derivative of B, a constant, times Y divided by A squared plus Y squared. So A and B are constants. And if we do the calculations, we have minus A squared plus Y squared divided multiplied by B minus 2Y times BY divided by A squared plus B squared squared. And that simplifies to Ey equals to y squared minus a squared multiplied by b divided by a squared plus, I made a mistake here, this should be y squared to the power squared, raised to the power 2. So the electric field vector is equal to y squared minus a squared times b divided by a squared plus y squared j. So the electric field has only component along y direction. Section 8. Electrostatic potential energy, the electron volt. 1 electron volt, EV, is the energy gained by an electron moving through a potential difference of 1 volt. 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. The electron volt is often a much more convenient unit than the joule for measuring the energy of individual particles. Section 9. Cathode ray tube, TV and computer monitors, oscilloscope. A cathode ray tube contains a wire cathode that, when heated, emits electron. A voltage source causes the electron to travel from cathode to anode. The electrons can be steered using electric or magnetic fields. Here we have a heated current that generates the electron from the cathode, passes through a grid and anode toward the anode, and they start accelerating with the help of two plates in horizontal deflection plates and two vertical deflection plates. We can orient and direct the electron toward the fluorescence screen, where the electron hits on the fluorescence screen toward this path and makes the spot bright on the screen where the electron hits. Televisions and computer monitors, except for LCD and plasma models, have a large cathode ray tube as their display. Variations in the field steer the electrons on their way to the screen. Here we can see the path of electrons from left to right, and their dashed line moving back to the left start to steer from left to right, and does this to complete the whole screen at rates of about like 50 to 60 hertz. To complete the whole screen, and then repeat the same procedure for the second scene or the second slide of the display. An oscilloscope displays an electrical signal on a screen, using it to deflect the beam vertically while it sweeps horizontally. Summary of Chapter 23. Electric potential is potential energy per unit charge. VBA is equal to delta V, which is VB minus VA, and that is equal to electric potential UB minus UA divided by Q, and that is the negative, the work WBA divided by Q. Potential difference between 2 points VBA equals to VB minus VA, and that is equal to minus the integral from point A to point B of electric field E dotted with dl. Potential of a point charge is equal to 1 over 4 pi epsilon naught times Q divided by R, and that is assumed for a single point charge. We assume V is equal to 0 when the distance R is equal to infinity. Equipotential line or surface along which potential is the same. Electric dipole potential is proportional to 1 over r squared. To find the electric field from electric potential, we have to take the derivative along each direction. So we have E sub x is equal to negative partial v partial x. E along y is equal to minus partial v partial y. And E sub z equals minus partial v partial z.